Student to the lesson of Lagrange multiplier. In this video, we will solve two questions about optimization problem where we will use Lagrange multiplier technique and method. If you haven't seen the previous parts where we discussed Lagrange multiplier, I strongly advise you to pause this video and go back and watch the other videos on how we use Lagrange multiplier, because we will use the same technique to solve an optimization problem. Now, for our question, we need to use Lagrange multiplier method to find the dimension of the rectangular box. So I will start off with a rectangular box, something like this. This one here, and this. So rectangular box has three dimensions. We have x, we have y, which is this one here, and this one here, and we have the height, which usually we will use the letter z to describe the height. Now, those are x, y, z, those are the dimension of any box, but our box today is a special one. Why? Because we need to find the largest volume. So it's a box that has a largest volume, and the surface area is fixed to be 64 inch square. So what we know here is that we need to find x, y, z such that we get the maximum. Remember, largest will translate into the maximum volume given. Now, when I say given, it means I have a constraint. So given the surface area as 64 inches square. So if we translate this, what I've just write here, into a math equation, what we need to do is we need to maximize the function of the volume, so the volume function. And for today, just let me use the same notation as before. It's a function, f of x, y, z. And what is the volume function? If I give you x, y, z, what is the volume? You just need to multiply them. So my function that I need to maximize is xyz, subject to, which is the constraint as usual, that the surface area equal 64. Now I need to write what is the surface area. Remember, the surface area is the area of the sides. So if you look at this box, first side we can see is this side down here. This is a rectangle. Usual rectangle has an area of x, y. But this one here is already doubled. We have one in the bottom, one in the top. So here we'll get not just xy. What we'll have is 2xy plus, we have one side here between y and z, and it's already doubled in the both side. So you will get 2yz. Finally, we'll have one part here, the one in front of the screen, and we have one in the back of the screen here, which is between x and z. So we'll get 2xz. And now this is a similar question to Lagrange multiplier. You have a function f, you have a constraint, usually we call it g of x, y, and z. So this one here, we call it g of x, y, and z. And we need to use Lagrange multiplier. So let's, at least before we go and solve the whole question Lagrange multiplier, let's write the equations, maybe discuss them and see what we will get. Now, to use Lagrange multiplier, remember we have to do three equations. First of all, fx equal lambda gx, fy equal lambda gy, and finally g of x comma y comma z equal to the number k should be the same. let's start with fx. Now remember, the function f is xyz. If we derivative with respect to x, we get only yz. And if we don't forget the z, so it is 4 equation in 4 variable. So first we get yz equal lambda. Now what's the derivative of g with respect to x? It is only y plus z. Second equation will be just xz equal lambda x plus z. Third equation will be xy equal lambda x plus y, and above all, don't forget the constraint itself, 2xy, 2xz, 2yz equal to 64. Now, system of 4 equations. All what we need to do is we need to deal with it in a clever way, in a way that really make things easy for us, and we need then to find the answer. So solving the system is something different than the question. All what you need is to put all those together and solve the question. So I will leave it for you. What I want you to do is please write for me in the comments the answer. What is the value for x, y, z that we will get 64? Then we go now to the next question, which is, again, we want to use the Lagrange multiplier to solve an optimization problem. Remember, optimization problem such as the one in yellow, we have seen it in the previous section, where we can use the second derivative test and the critical points to find the maximum and minimum. But in this question, we want to see if Lagrange multiplier can give me also an easy way. So in this question, we have a surface and we need to find the point that is closest to the origin. So the goal here, we need to minimize or find the minimum the distance function. Now what's the distance function? It will take, let me also call it f of x, y, z. It is big square root between, since it's the origin, so I will have x square minus 0, y minus 0 square, and z 0. Now, if you remember, when we deal with the distance, the minimization of the square root, it will be the same as if we just minimize the function itself. So for now, it is safe for me just to leave the square root for a minute, find it without the square root, and whatever the answer we find as a minimum distance, we will take the square root. This is an increasing function, so the minimum for the function and the square root of itself is the same. Of course, there is a condition that x, y, z, they satisfy this function, x, y square, z cube equal to 2. And this is, we call it g of x comma y. So we have this question here. And if we use Lagrange multiplier, again, we have to write set of equations. The first one is fx equal lambda gx, which will give me directly that 2x here to the left equal lambda. And then we can do the derivative of g, which is y square z cube. Fy equal lambda gy, and that will give me directly 2y equal lambda 2y z cube. And then we have fz equal lambda gz, and this give me directly 2z equal lambda 3xy square z square. Finally, we need to write the g as is. Okay. So you'll have to keep that in mind. We have to keep this in mind, that xy squared z cube is equal to 2 throughout the solution. Now, how would we try solving this question? I will leave it, of course, for you to solve it by yourself, but at least I can give you the idea. What if we start with equation number 2, take it to the other side, and take y as common factor? What will happen is we will have one option that y equal to 0. We can continue with that option and see where we will reach. Or what we will get is, of course, 2 and 2 will cancelled. We will get that lambda x z cube equal to 0. So we'll have so many cases, either y is 0, x is 0, z is 0, or lambda is 0. And once we start from that, we can also finalize the matter here. I will leave it for you to try it by yourself, and if you can, please write in the comment your answer. Thank you for watching.